Okay, here's our video today. Cherenkov Radiation. Sounds like a fancy name, right? How an electron beat light. And we should actually say how it beat a photon. Because photons are light. So let's write that out there. Get my pen working here. So instead of saying light, well, photons are light. And there's many types of light. It's part of the electromagnetic spectrum. And I said this before in other videos in physics. The electromagnetic spectrum is because light, these photons, will give off electric and magnetic fields, which we'll talk about in this video. So, you have radio. Radio waves are light. We can't see them. And microwaves, they're light. Can't see them either. And infrared is light. Snakes have infrared vision. And we only see this visible light. We'll just say VL, the visible light. That's the only light we see. And there's ultraviolet light, UV. Birds can see that. And then, of course, we get into X-rays, which are light, and gamma. So this is all part of the electromagnetic spectrum, and this is light, right? And these are all photons, and they're all going the same speed. Nothing is faster than light, right? We should say nothing in the universe, in our universe, is faster than light. Or we can say then photons. Of course, we can also talk about gluons. Gluons might be able to reach that speed, but we'll just talk about photons today. And so nothing in the universe is faster than photons, and we're going to say in a vacuum. Not a vacuum cleaner, by the way. In a vacuum, the vacuum of space, nothing is faster than photons. But something very important to know is that light will slow down in different mediums. So the medium of empty space, the medium of this vacuum, light will go 186,000 miles per second. That's extremely fast. It will slow down in water, it will slow down a little bit in air, and so forth. Now think about this for a minute. If you snap your finger, and I did this in other videos, you snap your finger. When you're snapping your finger, light could travel around the world 7.5 times. It's amazingly fast. It's 6 trillion, almost 6 trillion miles in 1 year. Think about this if you want to think about 6 trillion miles. If you go from Earth to Pluto and back, and you do that over 800 times, that's what light will do in a year. It's amazingly fast. Think also about light. Well, let's clear this out. Clear this out a little bit. And here is how light is moving in waves. You see it has a magnetic field and an electric field. And I'll talk about this in a minute, how the photon is moving. But if you think about it, from the sun, and we'll use yellow for the sun. Why not? So we have a sun. Here's from our sun, this yellow sun. And as photons are traveling, we'll make a little planet here. Let's say that's Mercury. Of course, we all know this is not to scale, right? Mercury. So light takes 19 seconds to get from the sun to Mercury. It's pretty fast. And if we say Venus next, and then we say Earth, and we'll put in Mars and so forth. Maybe we'll throw Jupiter in there. That's the next planet. So we know that light, get a yellow line back again. We know that light going from the sun to Earth takes 8 minutes. Get our color back in there. A little over 8 minutes. 8 minutes, 19 seconds. And to get to Mars, it takes 12 minutes. And the Jupiter takes 43 minutes. So if the sun blew up, which it never will because it's only a yellow dwarf, it's not big enough to blow up. But let's say, hypothetically, it did, we wouldn't know for 8 minutes and 19 seconds on Earth. But if we had a spaceship on Jupiter, we wouldn't know for 43 minutes. But if you can Think about how fast light is. It's extremely fast. People think sound is fast, but light is extremely more faster. If that's even an English phrase. Think about, like I said before, if we snap our fingers, light can go around the world 7.5 times in 1 second. Light. But sound would take 100 days. So light, which took 1 second to do 7.5 times around the world, would take sound 100 days. That's just to tell you how fast light is. So now that we know that light is fast, let's go back. Right? How does this all fit with Cherenkov radiation? How does this all fit in? So, as you can see here, there's these waves. Let's get the pen going. So as the photon moves, and it's moving, we'll take that color. You see, as it moves this way, it creates a field. And this field is creating these parabolas, right? It's creating this like sine waves. And as the field, let's say we'll start here, as it goes up here, making its magnetic field, at the same time, it's also creating an electric field at the same time. So let's clear that out. Let's do it again. So let's say in blue, we have, and we'll start here. As this is moving up, creating an electric field, the same time in red, it's creating a magnetic field, and so forth. And it's doing it at the same time that the proton is moving. Photon, not proton. Photon. So it kind of moves in these waves. When the photon hits water, and this is what we're going to talk about for this radiation, when the photon hits water, it will slow down. Slow down. The photon starts slowing down. And you've probably seen these in science class with refraction. Let's get a picture of refraction, actually, because in refraction, light will bend. And you wonder, why does light bend in water? It's because light slows down. So if you had this, whatever thing you had here, it would look like it's a little bigger and bent. And it's bent. This is an illusion. It's bent because light is slowing down in water. So it's going to go from 186,000 miles per second to about 144,000 miles per second. Still extremely fast, but it's slowed down. And that is the reason why, and we'll get into what happens now with Cherenkov radiation. All right, we're almost there. We have to talk about one more thing, cosmic rays. Write it over here. Cosmic rays. The rays that made the Fantastic Four, if you know that comic strip, right? So cosmic rays are these very high, extremely high particles. And mostly we're talking about photons here. They're highly charged photons. They can also be helium nuclei, and we'll talk about that. They also could be electrons. So these highly charged particles, and for Cherenkov radiation, we're really going to be talking about electrons. And we know that protons are already charged. They already have a positive charge. But cosmic rays, the photons in a cosmic ray have a lot more energy than your normal photon. And the same will go with an electron. So these cosmic rays, they come from deep space. They're coming from exploding stars. And they have enormous amounts of energy. And they enter the Earth. So these photons will enter the Earth. And when they enter the Earth, they'll combine. They'll knock into, of course, what we have in our atmosphere. They'll knock into oxygen. And they'll knock into nitrogen. And anything else in our atmosphere, like argon, maybe CO2. So they're going to knock into these particles. That's the first part to understand. So cosmic rays. And by the way, these cosmic rays, or some people call them astroparticles, they are traveling close to the speed of light, but not to the speed of light. Because again, nothing can go faster than light. Well, there is something. The universe is actually expanding faster than light, but that's a different story. So nothing in the universe, like I said before, can go faster than light, but the universe itself doesn't violate that rule because it can go faster than light. But if you get hit by cosmic rays, by the way, they will damage your DNA. It's not something that you want to be near. All right, and here's our magnetic field, right? Our magnetic shield, if you want to call it. So all these, and it protects us from the majority of cosmic rays. So all these cosmic rays, which are very dangerous, again, they could be highly energized protons. When they enter the atmosphere, they could be highly energized electrons, which we'll talk about shortly. And I also mentioned they could be atomic nuclei from a helium nucleus. Now, let me explain that. Get the pen working. So when we think about hydrogen, for example, we'll put hydrogen over here. Hydrogen. So hydrogen is basically, if we use our Bohr model, it's just a proton and an electron. So if the electron escapes, it's just a proton. It's just a positive proton. And with a cosmic ray coming from exploding stars, for example, they'll have much more energy than a normal proton in hydrogen, for example. So these protons, we'll put them over here, they're bombarding the magnetic field every second of every day. And our magnetic shield blocks them. They also could be in helium. So let me just show you with helium. In helium, inside helium, I should have made it bigger, but inside helium, you have two protons and two neutrons. And that's the nucleus. And it's surrounded by two electrons. That's helium. But if this nucleus escapes without the electrons, then that's really called an alpha particle. And the alpha particle could have a lot of energy, which would also call it a cosmic ray, cosmic radiation. And so, if we just want to use a different color, they're bombarding the atmosphere also. And again, the magnetic field is protecting us. But even with our magnetic field, there are still cosmic rays coming in. Not that much, but they're still coming in. And that's when our atmosphere takes over. So, I talked about the gases in our atmosphere before. We talked about oxygen, nitrogen, and these cosmic rays will bump into them and they'll be absorbed. In a sense of they'll lose energy. And again, not all of them will bombard with these molecules. Again, some will still come through. So let's get a cleaner page here. We'll go back to this picture. Now we can't see cosmic rays, right? So we're just pretending we're seeing them coming through. So again, if the magnetic field will protect us from the cosmic rays, those that get through they'll start bombing into O2, get our pen going, oxygen and nitrogen, argon, any other chemicals in there, and they'll lose their energy. And so, for example, if we just take oxygen, for example, so oxygen will become a positive ion. The cosmic rays, whether it's a proton, for example, will lose its energy to the oxygen. It'll become a positive ion. The electron will become free. We'll say the electron, or the electrons in oxygen will become free. They're free to roam around. And these free electrons now, with a lot of energy, extremely high amount of energy, so we'll just say electron, they're secondary cosmic radiation. And they could bump into other atoms within the atmosphere, other molecules, but some will make it to Earth. And when they hit water, this is where we're getting now to our radiation that we wanted to talk about. Let's get water going. All right. So now the electrons now, these high energized electrons, negatively charged, are now hitting the water. And like I said before in the video, light will slow down in water. Now, light aren't the electrons, but the photons in water will slow down. So when this happens, and let's write Cherenkov radiation on the top here. When this happens, the electrons will interact with the magnetic and electric fields of the photons. and they can actually exceed 144,000 miles per second, these electrons. This is when the electrons can travel faster than light, only in water and only through cosmic rays, these secondary cosmic rays of these electrons. And when they hit these magnetic fields, you know, the electromagnetic radiation of blue, the blue spectrum, will shine out, and some people can see this. Of course, we don't always see it. It has to be detected most of the time. Astronauts have said they have seen it. You'll see a blue glow. So let's write that down. Maybe we'll use green. So Cherenkov radiation. A quick review. It's when highly charged, electrically charged particles, in this case the electron, the negative charged electron, that is a secondary cosmic ray, has entered the water. And it will travel. When it travels faster than light, it can't travel faster than light in a vacuum, but it can travel faster than light in water, these cosmic rays. And when it does that, it's going to disrupt the electromagnetic field of the photon, and you'll see this blue radiation, which is the blue part of the spectrum. And let's get back to that wave. So let's use red here. Let's just pretend that the red is the cosmic ray, the cosmic ray of an electron just interrupting this magnetic field here, and so forth. So what it will do, it's going to cause the photon within this field to release. The photons will be released, and of course photons will release this energy that's involved in this field, will release more of the blue light, because our eyes see blue better, and blue has a faster, well, not a faster speed, but has a shorter wavelength, and so it'll scatter the blue to our eyes. That's why we see it as blue. So let's see if I can make this a little clearer. So the electron, this cosmic ray, now we'll call this electron, this highly charged electron, which is a cosmic ray, a secondary cosmic ray. It's going to disrupt the water molecules in the water, right? The oxygen and the hydrogen. And when it does that, photons will be released. Just think when you throw a rock in water, right? So let's say this was water. Should use blue, right? Here's the water. And when you throw a rock in the water, let's say here's the rock, right? And what it'll do is it'll create waves. You've seen this all the time, these waves. So in a sense, these waves are these shock waves. And again, these are the photons being released. And these photons will emit these waves of light. And the reason why it's blue or violet is because blue and violet have higher frequencies. When you look at the electromagnetic spectrum in visible light, red has the longest wavelengths and violet has the shortest. And blue's right over there. So our eyes see blue better than violet. We have blue cones in our eyes. So that's why we see blue. All right. That's our video today. Oh, and again, the electrons will travel when they do this, when they hit the water molecules. The only reason that the photons are releasing this light is because the electrons are moving faster than light in water only, not in a vacuum. And the only reason they're moving faster than light is because they have this cosmic radiation, this enormous energy that they got from space.